Hello. Very good. Hello, thank you very much for the invitation. I'm very happy to be here. It's my second time in Seattle, second program I'm attending. This time I'm going to talk about, well, also about turbulence, but in a slightly different context, in the context of, or in context of those systems, what we could understand as similar to turbulence, basically. I will try to make a little bit the link between heavy ion collisions and other scalar models that I usually use, GPE, radius scalars. And of course, lots of things have been done in collaboration. I will also, if we get to that, I will also discuss a few very preliminary results that are not published yet, but it's time to share them to the world. So the problem is a bit ambitious. I will start with the motivation, where I also kind of set up the language and also give links to turbulence, as one knows the influence, for instance, a little bit at least in this direction. Then I will go to work that has already a couple of years or dates a couple of years back already, but it's still interesting to understand this kind of turbulent behavior in closed systems, and this gives also the link to heavy ion collisions. Then I will go to scalar systems, where I also will discuss a little bit, which has been discussed in depth by Thomas Gassenzer, I think the first week, but I will discuss a little bit from a different perspective, and I will discuss spectral functions and their applications. And of course, as always, please discuss and ask questions, interrupt me whenever you wish. And I will probably jump over a few of the things because, again, it's a bit too ambitious, I guess. Okay, so let's start with motivation. So what I will be interested in are only closed systems, as I said in the beginning, and systems that are far from equilibrium, in the sense that we look at large occupation numbers, but weak couplings, and we are in this highly occupied regime where we can basically use classical or truncated Wigner simulations. So all of what I will be presenting will be are done with those truncated Wigner simulations or kinetic theory where applicable. I will discuss actually all of, I will not discuss the universe as an application, but I will discuss Boguslavski scalar theories, I will discuss GPEs, and I will also discuss longitudinal, basically gauge theories.
When you say highly occupied, do you mean that particles in the phase space, that many particles in H bar?
Yeah, exactly. So basically F gives you the occupation number, which is kind of understood as dn over the phase space, dx3, dv3. And if this is of order of 1 over coupling cluster, or at least much other than order 1, then you can apply those techniques, and then this is what I understand as coupling equilibrium. Okay, now
the real situation is, of course, F is only much larger than 1 in some region of phase space, right?
Okay. Oh yeah, of course. Just for, but this is just for momenta up to some certain momentum that basically dominates the dynamics. But but this is basically also the so when you talk about classical simulations or truncated Wigner approach, then one can also derive that having this kind of approximation or having this kind of condition that you have certain momenta that are dominating the dynamics up to some certain momentum, and if all the occupation numbers up to that momentum are very highly occupied, then you can actually derive that the classical approximation is a good approximation. It's very close to the absolute quantum world. I will not discuss much about. I mean, this is basically many of you are using GPEs or are acquainted with the classical statistical approximation or truncated Wigner approximation. But let me just say a few words because the language may be a little bit different. Now we are of course on a lattice, and the point is at first we initialize at some initial time, which we just call T0. We initialize the field. So we have classical fields, but in the beginning we think of them as quantum fields. And what we do is we initialize basically the 1 point, the 2 point functions, and in general one could also initialize more, but this is usually enough. So these are so-called Gaussian initial conditions, and so initializing that one, the 2 point correlation function, is actually important to mimic a distribution function, basically, because the phi and correlator or the psi probably, it depends on the theory, is connected to the distribution function quite straightforwardly. And this defines a wave function, basically. And here we have not done any approximation yet. We have started with basically quantum state. The approximation comes at the level of the equations of motion. So basically, we take the classical equations of motion and interpret them as the classical analogon of the Heisenberg equation of motion. Basically. And this is our approximation. And then this can be used for GPEs, for scalar fields, and so on. And then in the end, to get actual observables, we just average them over the initial conditions, over the initial wave function, basically.
But in this way, you don't have collisions, right?
Oh, we do.
But if you have GPE, you don't have.
No. This is the point. GPE is not meant to be only the first correlation function, but actually it has. So over time, it will have infinitely many correlations. So correlation function is more.
Same thing as the collision.
No, it has both. You can show analytically that Boltzmann collisions are part of the GPE. We had actually this discussion that the 2-to-2 scattering, for instance, and you have the. I will show you.
You shouldn't think thermalization would be after that.
No. It's not about. It's not about thermalization.
If you have the collision, you can always reach thermalization.
No. No.
Depends on whether it's classical scattering.
Exactly. So I have for that case actually a backup slide already. So basically think about sonic kinetic theory. In sonic kinetic theory, this would be a 2-to-2 scattering integral, and where you can think of that this matrix element is just your collision current, or your matrix element. That can be whatever theory you have. However, the main structure is that you have those gain minus loss structure, where these are occupation numbers, and this is a quantum and classical. So this is basically your 2-to-2 scattering, and this thermalizes. Now, the classicality condition just means that
That's right.
those X, those no.
It's not in GPE.
Exactly.
That's the series Varenda and so on did. You see, they had a special equation for that, the GPE on one side, and then the kinetic equation.
You mix up the thermal state or close to thermal state. So coupling of the GPE to a close to thermal state background to an extended field theory. So basically, we have a classical field theory. The GPE is in this case not meant as a condensate having only a first moment or first correlation function, one point correlation function, but it's actually a 2-point correlation function or whatever, and that has quasi-particle excitation. It is not only a homogeneous or inhomogeneous, but only X-space dependent thing. It has also fluctuations inside, and you can use those fluctuations to define a distribution function from the fields, as I said, the phi correlation function defines a distribution function. And you can show analytically that this collision integral is part in the description by basically going from f+1 to these kind of approximation. This is part of that. And I will show you much more examples of how you can use kinetic descriptions to approximate the field theoretical.
So when you say approximation, it's the approximation of the like that our motion is described by a Schrödinger equation, but you say no, it produces even the second law in the classical limit. This is exactly the type of approximation. You're throwing out 1 compared to a number which is 10 to the 23. So
Yeah,
roughly speaking.
yeah, yeah. So roughly speaking, yeah.
So, I mean, I wouldn't call this an approximation, it's a classical limit, so.
Okay, sorry. It is the classical limit, basically.
Because everything is exact, essentially.
Yes.
You know,
Yes.
so numbers of 1 and 10 to the 23.
This is right. I mean, in this sense, yeah. Sorry. Yeah, in a different. It depends on the community. In some communities, it's really an approximation. Other communities, it can be a. Anyway, yeah.
Just like the Newton's second law is an approximation.
Right. Right. Exactly. Okay. But I will come back to this question a bit deeper, and so on if we have time. All right. So let's get back to. Okay. Very good. So okay. Now, what are we after? We are after. We try to understand general states in those class systems. So basically, you start with a highly occupied system, which means that your phi basically or psi correlation function is initially large, or also after some time it stays large. And if the system is closed, which means that you have no dissipation, what usually forms, and this has been shown in many different system theories. Sorry?
It's a Fermi distribution. Why that?
It's not a Fermi distribution. It's
It's a step function. It's a Fermi distribution.
no. Look. This is only one way.
What the shape is, the multiplication probability is bigger than 1, but it's a Fermi
No,
distribution.
you can take any shape. No, please don't.
Why
sit
the
down on
shape?
it.
Why the
You can use any shape. It just doesn't matter, because after some time, the details of the shape do not matter. You get into a attractor. Sorry?
What's the relaxation?
Oh, it's very quick. Relaxation time to the sense of getting to this kind of attractor is very quick, and I don't have numbers at the moment here, but I will show you already being at this attractor, at this fixed point. So don't misinterpret. This is only a schematic thing. The initial condition can be whatever you wish. It can have a peak. It can be whatever. The important thing is that the characteristic distribution is very large, of the order of the inverse coupling. And what happens very quickly is that you basically start with what we call in this sense buffer equilibrium initial condition, and before going to thermal equilibrium, the system takes a detour, and it approaches a so-called non-thermal fixed point, which is basically just a fancy name to say that that exactly the knowledge of your initial conditions gets lost. You become very insensitive to the time scale, and the dynamics becomes self-similar, which means that you have a distribution function, which is in general a function of time and momentum, that becomes a scaling law. So you can scale out the time, it becomes a power law in front of that, and you get a t to the beta p. And now getting one step further is, so this is, for instance, an example of a specific system that I will actually also be talking about a little bit further. So when you think about those self-similar evolution, it's not only an alpha, so you don't only have those exponents alpha, beta in the scaling function, but the scaling function itself at low momenta, or at lower momenta, at least in this example, behaves as a power law, p to the minus k. And then you can think about what is actually this k, what is actually this exponent. And what it turns out that when you think about when you think about this system with dissipation, basically a steady state system, then it turns out that the k is very close to the actual turbulent spectral exponent. So what you have in those systems is usually you have exponents alpha beta, which are universal, so they are not dependent on the initial conditions. They just arise from the dynamics automatically without any fine tuning. And you have a universal scaling function. So also this grid is universal. So you can rescale your occupation numbers and the momenta by rescaling momentum and occupation numbers according to those power laws, and you will see that this form stays the same. And at some point, so you have usually power laws. So this is now a direct energy cascade. I will also show you the example when you have the inverse, an inverse cascade, and then the power law will be basically here, and this will be something that is connected to this kind of thing. Yes.
Can you just go back one slide?
Yes.
One question. So obviously you have this self-similarity regime when you do it, but you have these blue arrows. So what determines whether you actually go through a non-thermal fixed point? Is that something you will say more about? Or?
Right. Well, I can actually say that already, because what determines is following. So if you have a purely classical system and an infinitely large, and an infinitely large volume and an infinitely small lattice space, unless if you are in the continuum limit of a purely classical system, it will always be closer and closer to non-thermal fixed point. It will eventually end up there. But the point is that the physical system is not infinitely classical. We have quantum fluctuations, which are basically the order 1 distribution. So you have a quantum vacuum that you have neglected basically here.
Place you could go on principle,
Sorry?
which is classical thermal equilibrium.
Yes, exactly. So, but this is not the quantum thermal equilibrium we talk about.
I understand, but ordinarily people would say that for classical systems and ergodic theorems, they should go to classical thermal equilibrium if you waited longer. That's what I learned in my textbooks when I was a graduate student.
Yes, this also happens.
That's not on your plot.
That's not in my plot because classical thermal equilibrium is of course not the quantum equilibrium state you would like the system to get. It's not physical.
So classical, should I comment on this? Because I think it's a very important point. Because the thermal equilibrium for a classical system has the so-called ultraviolet catastrophe.
The Rayleigh-Jeans divergence, yes.
Right. So actually, this determines the direction of your energy cascade, essentially. You want to put all the energy in the classical system to infinity, right? And then eventually, this divergent distribution is cut off by quantum effects.
Right.
When the occupation numbers become a 1, then you have to switch to the quantum description and all this. So
This is exactly.
right. So on one hand, it determines the ultraviolet catastrophe determines the essentially direction of your redistribution of energies. If your energy is predominantly at small, wave number scales, then it has to somehow be delivered to those long scales. And on the other hand, eventually the problem is regularized by quantum mechanics.
Exactly. So basically, when you have order 1.
It's a very interesting point if you dominate
Sorry.
I think his point is a very interesting one. You see, there is another point you see concerning the distribution here. I can integrate all the momenta, and then the question is, the integral does conserve in time or not? Because if it does, then there is a correlation between alpha and beta. Alpha is 3 beta.
Exactly.
Otherwise it's not.
Sorry, this is what I have not said so far, but this is exactly what happens. So there's not no fixed points.
So you don't have two critical exponents. You have only one.
So look, it depends on the region. So here is an example of a direct energy cascade, which means that energy density in this region is conserved, which means that when you have omega of p times f of p, and you integrate over momentum.
No, I can integrate f alone, particle number.
No, look.
That's a condition.
Look.
When I integrate the energy, I have another condition. They might be not consistent with each other.
They are not consistent. This is the whole point.
Okay.
So this is the whole point, that you have a conserved quantity in one region, but you can have another conserved quantity in the other region. Indeed, this is what
you're saying, that in one region of momentum you conserve particle number, in the other you conserve energy.
Exactly this happens.
Okay.
And
then
this,
you have two different conditions on alpha and beta. Right?
Exactly.
So one condition there, another one.
Absolutely.
Okay.
So in this case, in the context of relativistic scalar theories or gations which are also relativistic, or relativistic gations, then what you will have is that at high momenta you will have alpha equals d plus 1 beta, which is exactly the condition you said, which corresponds to energy density, conservation. While for scalar theories, again, I hope I get there, you get the other thing, you get the integral d3pf or ddpf, which gives you an alpha equals d beta condition, and this is very, very well conserved. So basically, in the end, you have what determines everything is you have a conservation law, which gives you a relation between alpha and beta, and then you can determine by using a basically kinetic description. This will give you a second relation between alpha, beta, and whatever. But this is really dependent on the kinetic or on the dynamics, basically. Yes.
So just going back to my original question, which is related to all of these flows, but so the flow, the bottom flow here, if you would start with something which does not have classical conditions, but has, let's say, quantum conditions, then you don't go through a non-thermal fixed point. So it's only because of the sort of inadequacies, let's say, of our initial guess of the solution that we actually go to this non-thermal fixed point.
I think it's more the Hamiltonian law.
Well, it may not be the
Coupling concept
inadequacies.
is very far away.
It may not be the inadequacies of your, it may be the physical situation is that it's a highly occupied state to begin with.
Exactly.
There are examples of physical systems.
I will go to that in a minute.
It could be the coupling concept, it's such that it's very far away from the thermal point.
Yeah, but it could be that there are physical systems where the
You mean initial conditions?
Yes.
and initial
Exactly.
conditions
So coming back to your question, actually, I'm sorry, I have not thought about that, but this is meant as a quantum situation. So what I showed here is not the classical limit of this thing. This would be a different diagram, but it is supposed to be the actual physical quantum world. So basically, close to equilibrium, what I mean is basically a small quench from the actual thermal state, basically changing a little bit the temperature or something like that, which is of course not feasible in a classical approximation. Classical approximation just breaks down there. But then you of course have kind of a relaxation to thermal equilibrium. While for certain conditions or in different physical situations, you have those far from equilibrium initial conditions, as Larry just said, and you get to this thing. So let's actually look at some of those examples. And the first example will be, example 2, because the other one was the first example. Anyways, one example will be actually heavy ion collisions. And now what we think about in heavy ion collisions are two nuclei colliding, and they are very thin because of Lorentz contraction, basically. And after the collision, you get a very highly correlated system. And you can describe it with very, very large fields that Larry was part of, that Larry has, for instance, also described in his papers. And this field behaves in a very, very highly correlated way. And then the dynamics becomes basically classical at early times. And then you can evolve it even further and further, and at some point kinetic theory becomes available, and after a while actually hydrodynamics becomes available, and then you get this kind of fluid dynamical picture of basically of thermalized.
Do you get hydrodynamic behavior on F is much larger than 1?
No. Well, it's
Beyond yes or no?
No. It's not the hydrodynamic behavior you mean. It's not near thermal equilibrium hydrodynamic behavior. It's not that much as you want. However, at the non-thermal fixed point, this has been done by Alexis and Jürgen Bergers. This is a very, very recent paper. You can write hydrodynamic descriptions around a non-thermal fixed point. This is a completely different story. It's not the hydrodynamic behavior you mean, but I just wanted to add that.
So what is that?
Sorry?
What is that behavior? It's not regular hydrodynamic. What is that?
It's basically looking at your momenta based or moments around a thermal state instead of around the thermal state. But anyways, this is a different story. So no, this is far from equilibrium. You don't have hydrodynamic behavior. This is basically a late time limit of all that, which is not classical.
I didn't see the far from equilibrium. Say F smaller than
1.
one.
Which is already
No, equilibrium, close to equilibrium. That's my question is.
F much smaller. No,
So
so
the
F,
Pascal regime.
F
So
of
yes,
the
F larger than 1. I'm sorry, F larger than 1, but you're close to equilibrium, thermal equilibrium.
No, you are not. I mean, this is basically excluded. So if F is much larger than 1 for typical modes, then you are not close to equilibrium.
The conversation is there.
No,
So,
I mean, these are different regimes, basically. But I mean, this is much more complicated than what I'm going to tell you. I will just tell you just an early stage. So there are many stages in this evolution. And we are in the recoupling limit. So we think of extremely high energies where basically your fields are of order 1 over coupling, and you have mainly gauge bosonic fields. Now what happens is that so starting from this kind of highly occupied system, large fields, what you get at is you get some kind of self-similar evolution. Because you are anisotropic, you got actually power loss in transverse and longitudinal direction. So basically, you have an expansion in the z direction. You can imagine, which gives you an isotropy in momentum space. So you have different exponents for pt and pz. And what you also see is you can also look at the distribution function and at the different scaling exponents. So to make the story short, you get for alpha, beta, and gamma for many different initial conditions. So you can play around with initial conditions. You get always this kind of set of scaling exponents. And
sorry, what's the dimensionality here? Why you have what's there? Is it 1-dimensional or 3-dimensional?
It's 3-dimensional, but you have one expanding dimension. So basically, you have this metric tensor which is expanding, which is a little bit different. The reason for that being that you change basically your coordinate system, and you end up with that. But the important thing is that you get a turbulent-like behavior in the transverse direction for transversal measure, which gives you 1 over pt power law, and you have an interesting shape which turns out to be Gaussian in pz direction.
and if that universal behavior conserve energy but not particles.
Actually, here you can conserve both.
You can't do that.
No, you can, because you have now more degrees of freedom, and the system. This is what happened out of that, right? It just turned out that that particle number and energy density, and with that any moment, is conserved in this specific fixed point. And this is because sorry.
If I look at the particle number, if you integrate over the z, I get a prescale z, I get 1/3, and I don't get 2/3 until the alpha.
I'm sorry, t times f. You have to integrate t times f basically, and you have to rescale everything with proper time.
I think I could out.
But so basically in those rescale coordinates the system. So sorry.
It's actually, can I come
Yes.
to this? It's actually quite typical that you can serve both. I mean, you can serve both, but typically the situation is that the integrals for a particle number and energies, they build up at different scales. There's typically separation
But
of
there's
scales.
another scale.
No, you have self-similar solution, but it's self-similar solution close to a certain scale. For instance, high energy scales. And
You mean
For
the
instance-
approximate conservation that is going to be.
well, I mean, it's approximate in the sense of there's quantum correction.
No,
Otherwise, it's always that.
I mean, is you particle number with the high scales, the energy of the low scales.
Oh, they're just irrelevant in terms of the integral, because obviously the theoretical
Okay,
limit is you have
okay,
infinite
I'll think about it.
We can discuss later.
We can say later, but here in this specific example, you have actually both at the same momentum scale sequence, which was also a surprise for us. But anyways, what was really a surprise, and this was quite interesting because what we looked at was a completely different system, which is a scalar theory, a lambda phi to the 4 coupling, or n symmetric. So we also looked at different but in the same geometry, in the same expanding geometry, in order to actually to understand a little bit better the gauge theory case. It turned out that the scalar theory is much more complicated than the gauge theory, but that's a different story. I will not go more into that. But what was interesting is that there was a momentum region, as you said, there are different momentum regions, and every momentum region has its own conservation laws, its dynamics, and so on, and it has its own set of exponents and so actually all of those sets can be different in different momentum regions. But there was one specific momentum region where you had all the exponents being the same for gauge theory and for scalar theory, so basically the same set here. and also the distribution function in transverse functional momentum was also the same, which made us conjecture that there is some kind of universality between
But
scalar
if
motion.
this is true, force of F 5 to the fourth in force of the GP equation, right? And then probably you can think of this, try to realize it, call that somehow.
This was actually the point here. So
And then that could be interesting, you see, because there'll be the audience check if you have all this.
this was the whole.
Especially the momentum distribution, you see, they can be measured. Be very specific. It's practical.
So basically, I think the paper was something from heavy anchorages to superfluid Bose gases, so which was also discussing the possibility to actually have that realized in optical data. So basically, having a heavy ion collision.
Wait, but this problem is well known, right? The non-equilibrium Bose-Einstein condensation has been around for 30 years,
I'll come to that.
right?
It could be well known, you see in a very small group of people. So it doesn't mean well known, you see widely. So you see,
But this is not condensation, right? This is not Bose-Einstein condensation here.
But the final state of the Gross-Pitayevsky equation is Bose-Einstein condensate, so.
Yeah, but this is
equilibrium.
in equilibrium. This is a
but
different.
anisotropic momentum distribution.
It's a completely different story from that.
You see,
But
transversal it's one and longitudinal it's another one. So you get different scalings. It's not P transversal per Pz squared. You have it's like you have an effective mass.
But it's just always expanding.
Yeah.
In one dimension.
Yeah.
And that's
I see, so, okay, so that's a different problem.
it's a different problem. But I will come actually to your problem, to the one you said, actually right after the slide. So
But is that kind of like expanding full depth? You know, when you're doing
it would be an expanding full atoms,
That's
yeah.
exactly the
Yeah.
problem.
Well, but one has to be cautious to have actually exactly this metric tensor. So at the moment, I'm not sure if this is possible at the moment because it's not like you really have to be in the other in this other metric tensor. However, people are thinking about that.
Yeah, okay.
Modify the tensor, metric tensor.
Yes, metric tensor has really to be expanded.
Well, if you do that, it's trivial.
It's not like giving a constant. It's like getting bubble expansion.
It's accelerated.
It's accelerating.
You
Yeah.
have to set it up right to do
I
that.
thought we don't.
Okay. Okay. Now, short intermezzo. We talked about non-flow fixed one already, and so the common approach is, as I said, classical ladder simulations or experimental observations. I will probably flash a slide on that. And the understanding comes from a kinetic approach. So basically, also this here can be understood within a kinetic theory, which basically is a comment also to your question before. So you can understand and you can actually derive all of those within a kinetic theory, and this was actually used to understand which kinetic theory is right. So, anyways, now what we will go on. So we discussed a little bit heavy collisions, and I don't want to go more in this direction. I actually want to get more into GPEs and scale models. Sorry?
What's GPE?
Gross-Pitayevsky equation. I'm so sorry. Everyone says GPE. That's why it's so short. So I will just. I'm very, very sorry. So
GPE was the problem. This GPE was.
yeah. Okay. So and so what turns out that there are some universal dynamics between different scalar theories. Now, so this is the picture of scalar theory, quite general. So for non-relativistic systems, for relativistic systems, and here we are really in an isotropic, non-expanding medium. Everything is as we know it, as you know, as can be also realized experimentally at the moment also, and we really look at very, very different scalar systems that can mimic different or model different different physical situations, and also non-relativistic scalars. And what you get is a dual cascade. So the picture of that is that you have at high momenta, basically above your chemical potential in your Gross-Pitayevsky equation, or above the mass for the relativistic scalar theory, you have a direct energy cascade where energy is the conserved quantity here, and you have a particle number conserved region in the infrared. the total particle energy is also conserved, but basically the non-conservation of particle number here and non-conservation particle energy here is somehow realized in this region. Basically, it makes all sense in the end. This is what I wanted to say mathematically too, because the dominating part for particle number comes from this part. So what happens here? And here we are really talking also about relativistic scalar theory that don't have this U1 symmetry of GPE, right? So they dynamically conserve particle number. Now, the region between those two parts, so basically between the particle number and the energy cascade, this region is basically driven by the inverse coupling. So basically, all of that is basically perturbative. In the sense of perturbative kinetic theory, all of that is very non-perturbative. And they are, of course, different scaling regimes, so different sets of alpha beta s. And this here is different in non-relativistic theories, of course, because your energy is also different. So for non-relativistic, you have p squared over 2m. For relativistic, you have basically p, so or square root of m squared plus p squared. Now, going more into this infrared region, what you find is that the infrared is self-similar. Now, this is shown as an example for d equals 3 and relativistic n equals 2. So O2's theory, and n is the number of components of your scalar vector, or sorry, your scalar. And what you find is that those dynamics have this kind of scaling exponents for different dimensions, for different basically different initial conditions, of course, and also different theories.
But it doesn't conserve energy.
This doesn't conserve energy. This conserves particle number.
Yes. Sorry.
So that's why it's alpha equals d beta. Exactly, particle number conserving. And the question is how to understand all of that. So first of all, what one finds is that the scaling, the functional form is pretty similar, actually the same in many different systems, and you can model that in this kind of form. But basically, this is an early time. It is not close enough to. So what I show you here is not close enough to the actual non-thermal fixed, which probably means that this should become flat at lower momentum. So that's why I wrote this part as kappa small being 0 to 0.5. But this is important. This is basically 4 to 4.5. So you have really power law here, and that's why people named this kind of regime as a strong wave turbulence, because you have basically a power law that can be connected to a turbulent setting where you don't have any dynamics in that. And it seems to coincide. Why exactly? It's still not completely clear, but it seems to coincide. And now the question is how to understand all of that. And you cannot use usual perturbation theory because your distribution functions, so the important distribution, the important occupation numbers are of the order of the inverse coupling or even larger, which makes no sense if you think about kinetic theory that is an expansion in basically lambda times f order.
But how can kappa lesser be 0?
Sorry?
How could kappa lesser be 0?
Oh, this is basically, it just means that this becomes flat.
Well, kappa lesser means 0 means it goes like 1 over p to the kappa greater, right? And that means singular small p.
No, it's, no. What do you mean by 1 over?
Well, I put in, I say kappa lesser is 0, ignore the first term. Then the second term is 1 over p
No.
to the kappa greater.
And I think
No,
the
but
first
it's a
term
one.
will dominate.
But that's a very small singularity. I mean, it's very.
Well, I don't know, but it's showing up on most of the spot there. That turnover is not a consequence of
So
1 over pt.
So this is smaller than 1 over p. So basically,
What exactly is plotted there? It's got some factors of heating or something? Is it out?
yeah, this is basically so this is This is plotted
I would have
as
thought the change in the power and the slope would have been one power compared to the other taking over, right?
yes, but this power can be whatever. I mean, it can be also just a constant, right? And what it turns out, so basically, one can write down an effective kinetic theory by resumming kind of vortices
Yeah.
and
What I'm confused about it, if it was one power, I would have expected it to.
this is so for high momenta, this part dominates, right?
Right.
That's why you have this
You
e to the
said
minus one.
that kappa can go to capital S or can go to 0. So that entire region where the slope is changed.
Yes,
is like down.
this would become constant, flat. So kappa 0 being 0 means that this is flat.
Oh, you mean there's a constant there? I see. I see.
First
Yeah,
goes
yeah,
to
this is
constant,
sorry.
not zero.
So basically, well, this is not completely conclusive because there has been another simulation that suggests that this becomes constant. Then also kinetic theory suggests this becomes constant. We see that it's slightly non-constant. That's why this is a little bit not completely clear. But this is a small thing basically. Yes, so it can be
Sorry,
constant.
this is stupid.
No, I'm sorry too. So in order to get a kinetic theory, what one can do is one can systematically derive the kinetic theory by resumming all terms that come at a certain order in 1 over n, basically at next leading order, for instance. And then you can think about, oh, what happens at n equals 1? Well, I just use the theory for where I've done everything, and then I extrapolate to n equal 1 and n equal 2 and so on. And the funny thing is,
and like the number of colors.
exactly, the number of components of your scalar vector. Sorry, of your scalar.
So isn't large n the same as a mean field theory?
Completely large n, yes, but we don't go to infinite n.
Okay.
It's still a finite n effect there. And also in the Gross-Pitayevsky, you can think about different components, and you can also think about doing a 1 over n expansion. And what it turns out to be is, so you can do that analytically. You can and then you can derive a kinetic description for that with a pretty interesting. So you get an effective coupling, and you can simulate this kinetic theory. So first of all, you get those alpha and beta that I discussed here already analytically, and then numerically you can simulate your effective kinetic theory, and what you will end up with is actually a very similar distribution. But don't forget, this is just kinetic theory. So there are no vortices, nothing assumed in this kinetic theory, which is already funny because in the GPE you see vortices too. This is actually a big problem, still not completely solved, but I will actually discuss that in the last 15 minutes. And then there has been an experiment or actually 2 experiments on non-thermal fixed-point, and they have been experimentally observed last year. One of the experiments actually also found basically the same.
So this constant behavior for small pt is sort of a saturation.
Yes, it's sort of a situation. So basically, particle number is dominated here.
Yeah, well, the distribution is getting completely full. Can sort of constant phase space per unit.
You have basically patches, and they increase with time with the momentum, the typical low momentum going to low momentum. Okay, so I just wanted to flash that. Now, in the last 15 minutes, I would actually like to talk a little bit about spectral functions. Because exactly the question of what degrees of freedom are actually irrelevant for all of this different kind of dynamics. And as far as I understand, a lot is being done also using these kind of distribution functions or a momentum space correlation functions at equal time to understand what is going on. Now, the point we would like to, and of course, spectral functions and unequal time correlation functions, I think people are also using them, but quite rarely. But the point is that you get lots of information from that about the excitation spectrum and also eventually about the relevant degrees of freedom. So questions concerning, for instance, concerning what degrees of freedom are relevant, so basically at initial stage, at what stage what degrees of freedom are relevant, when can I start speaking with quasi-particles, and when kinetic theory becomes relevant? What about transport coefficients as functions of time? These are all questions that are connected more to unequal time correlation function. Basically, take a correlation function phi phi, but take one phi at one time, the other one at the other time, and this will give you much more information than from equal time correlations. And what we will be discussing is the spectral function, or basically gauge theory, not including QCD, but although we are also at the moment there is a project on also concerning fermions, but basically about gauge bosons and scalar theories. And at the beginning, for non-optimal fixed points, in order to understand what is actually macroscopically going on there. Now, when I'm talking about spectral functions, what do I actually mean? I mean, just as a kind of reminder, basically, a spectral function basically includes all possible excitations, and it's basically so for bosons, it's the commutator of fields. So for if you think about Boguslavski, then you would have psi dagger, basically commutator of that, and the expectation value gives you at unequal times. Then you can Fourier transform with respect to the relative time, go into frequency space, and then you see different structures. And one particular structure that you often see in these kind of things is our Lorentz field. So basically, peaks of the form of such a Lorentzian, which gives you a typical energy density, which gives you the dispersion relation, and a width, which is a damping rate, basically of your or inverse lifetime of your quasi-particles. But then you have also lots of different things that you can get of that, like unstable modes, which are in delta t space, or cuts, extra poles, whatever. There are many things you can get from that. Now, I would like to flash a little bit about gauge theories and then come to scalar theories. So, there is a new numerical method now to extract spectral functions in such classical systems, and so actually one of the first applications was to 3+ one-dimensional gauge plasmas in the self-similar regime that I've actually already talked a little bit about in the beginning. And I will talk about mean features of spectral and statistical functions, but there is a very similar method really used for Boguslavski equations by my collaborators that I will also probably flash afterwards. And then I want to talk a little bit also about relativistic scalars, which is still work in progress. And all of that will discuss exactly this non-optimal fixed point in the infrared that seems to be so universal, but when you look deeper into that, it has very interesting structure. Okay, well, let's start with the gauge theory. Or actually, let's start with the actual method. Maybe a little bit about the method. So what we basically do is we have a system. So this is now, for instance, a z=0 cut through your lattice of basically an observable like E squared, basically the electric field squared, but you can do that with any field. And what you do is you basically perturb it at some time with an instant source. So at some time you perturb it, and this is similar to just linear response theory.
So it's a delta function in time.
Exactly. And I think I have also a slide about that in the back, but I won't go through that. And once you do that, you can split your equations into the unperturbed theory and the perturbed theory. And the perturbed theory is basically, or the response is basically follows a linearized equation of motion with this instantaneous source. And then you can just evolve that, and you get some response. And from this response, from this response field, knowing the source, you can get the retarded propagator, basically. And the retarded propagator is like your spectral function. For gauge theories, you can also, for instance, look at different polarization. For scalar theories, you can also play around a little bit with the degrees of freedom and with the projections. And the spectral function is something that we would like to discuss. So just a reminder here Well, non-thermal fixed points. So what you're looking at is now non-ideal plasmas, where you have this kind of energy cascade, where momenta is going to higher and higher momenta. So where energy goes to higher and higher momenta, basically, you have a cascading picture, and this will be our testing system, basically. So in the beginning, I was talking about non-thermal fixed point, or the self-similar attractor, as a general state of your closed theory dynamics or closed system dynamics. Now I'm actually using those non-thermal fixed points to understand a little bit better about about spectral functions, about the method, and so on. Now these are already the results. So what I show you here is the spectral function for this gauge fields. So by the way, if you have any question, please ask. I might be a little bit rushing at the moment, but please don't be. Yes, you can just ask whatever you wish. So on the left-hand side, you see rho t as a function of delta t. Now, I have to say one more thing, right? Those two, so we are out of equilibrium. We're actually far from equilibrium, which means that all the fields are time dependent, really time dependent. Which means that what you would actually like to do is you would like to go from t to prime coordinates to central time, t plus t prime over 2, and delta t coordinates. Now, what we do instead of doing that, because this makes it a little bit more complicated to do Fourier transforms and to interpret the results, what we do is we actually go to very, very large t and t prime, and we look only at a small delta t extent. And this is a pretty good approximation of the dynamics, which means that we can do the Fourier transform and everything, and we can interpret our result as being at the time t or t prime, which are basically the same. Right, this is basically the approximation we did. Okay, on the right-hand side, we look at the Fourier transform. Now, for those gauge bosons, we see those oscillations for different momenta, and we see quasi-particle peaks, which is already nice. This has been also predicted, and what has also been predicted is that at low momenta, for frequencies below the momentum, there are certain cuts, Landau damping is there, which is kind of a continuum, and you actually see that in this method too. And now I have not talked about Hard-thermal loop theory, while you can apply that to. I have also backup slides for that. But Hard-thermal loop theory basically is a perturbation theory for thermal systems, and you can do that for gauge theories. And this has been done, and at leading order, so the results, the curves here are leading order results, and you see that they match the place, the location of the peak matches very well those, and also this damping rate matches the standard damping region matches very well. But the important information is that there is no fitting inside here. So the curves have been determined within HTL, and it's really a method completely perturbative or analytic compared to the completely numerical method here. And the reason is that we were sure that we can use HTL basically in this region because of some scale separation.
So HTL doesn't have a bit for the...
Yes, because it's a leading order effect. Now, you can go to next to leading order in HTL, but this is pretty hard, and this has been done. I have a backup slide here. This has been done, of course, but only for the first point p equals 0 and for the last point p at infinity, which basically gives you a huge error box. So what we get is actually, for the first time, a curve of your width, of your damping rate. That was so far very, very difficult to obtain, and has not been obtained analytically at all.
Which equations are actually solving numerically?
For this year, yeah, we are solving Young-Mills equations. I have not written them down here, but I have written them down here. So, but the lattice formulation of that. So it's basically the Young-Mills classical Young-Mills equation, but not for gauge fields MU, but for the links e to the power of I AV basically.
But I will, the hard-thermal assumed it was thermal, right?
Yes,
And you're not.
we are not.
So why are they the same?
It is possible because, yeah, I have to jump over that because
This was a big jump.
yeah, but yeah, exactly. But the point is, why are we allowed to use actually Hard-thermal loop theory is that in Hard-thermal loop theory, the main assumption is that you have a separation of scales, that your hard scale lambda is much larger than your soft scale, which is basically given by your mass. In thermal equilibrium, this is given by temperature, and this is given by G times temperature. Out of equilibrium, this is a different scale. This is your hard scale, basically. And the point is that the spectral function, for instance, that you obtain from HTL does not care about the form of F. What it cares about is about the value of your mass, basically, or other parameters, which you can derive again within HTL. This is an HTL.
That is adjusted so you get the hard-thermal.
It's exactly. This is adjusted, but you have to adjust it to be consistent. Yeah, exactly.
So if the mass scale, the problem's not the same mass scale.
Exactly.
Or you use for the thermal theory, but it's trivial kind of rescaling.
Exactly. Absolutely, yeah.
So the dispersion curve for these quasi-particle excitations looks very non-trivial, but what you're saying is that it's given by this m squared that you calculate with that formula you just showed.
Yes. You mean the spectral function, right?
Yeah.
Yeah, it's very non-trivial, but the form itself is really only a function of m squared basically, or of this mass. And using this m squared from this integral, you get this you get the spectral function.
Which one?
Well, you get the position.
You get the position of the peak, and you also get this Landau damping correction. So also the height, everything is really done by this one thing.
So you mind if I say wow? And that's pretty remarkable.
Yes. Thank you.
Yeah, very nice.
Okay, and I've shown you how we go beyond HTL distributing order by actually showing you the width, and you can do that for transverse and extreme polarizations and so on. Now let me also discuss one more bit, because before may I actually go to scalar theories?
5 minutes, please.
5 minutes. Okay, very good. Then I will be very quick. 5 minutes are enough for all of that, I guess. Okay, so the statistical so here we discussed different correlation functions. So the other one was spectral function. Now here we talk about basically this is actually quantum mechanical. It's an anticommutator of E fields or of A dot fields basically. But in the classical definition, this becomes only a product. And this is a different correlation function. However, in thermal equilibrium, these correlation functions are connected. So rho dot is basically a commutator of E and A field. This one is an anticommutator of E and E fields. And at low momentum, you just have fluctuation spatial relation, which trivially makes them the same, basically. However, out of equilibrium, this is very non-trivial. They are, in general, completely independent functions. However, it turns out that if you normalize this one properly, because of course physical function is proportional to the distribution, if you normalize it in the same way as you normalize spectral function, then well, they fall on top of each other, which is kind of something what one can call the generalized situation. Now, coming back, so having that in mind, coming back now to scalars in the infrared, and this is the last part of my talk, where we have GPEs that are scalars and realistic scalars, and we're concentrating again on the infrared. For just the Gross-Vitajescu equation that has been done by Sierra and Jürgen, what you see is what you see is, first of all, you see the spectral function in blue, and the statistical propagator, this anticommutator of side fields, in red, for different times. And what happens is that the statistical function has both peaks has two peaks, while the spectral function has only one peak. So the generalized fluctuation dissipation relation, even that is broken. Two different systems, two different things, right? So, however, so first of all, it's broken. So you see this transport peak at low momenta for the statistical function, and this is the dominating part. It turns out to be that is the dominating part of this infrared region. Okay, now what you would say probably, oh, well, we have this universality, so all scalar theories should have the same picture. Well, let's start with O1 theory, with a single component theory, and indeed you have the same picture. This is very preliminary still. Well, these are basically, so the data are not preliminary, but it's not out yet. So it looks the O1 theory looks very similar to the Boguslavski equation. But don't forget, the O1 theory has only one single component scalar, while the Boguslavski is basically two complex components, or two real components of one complex field. So one would actually think that this should be closer to an O2 theory. I will come to that in the last 2 minutes. So you see again that is the statistical function that is now, the definition changes a little bit, of course, from theory to theory, but it's very similar. So statistical function has two peaks, and at low momenta this peak dominates, while at high momenta the Boguslavski peak here, and indeed this is really the Boguslavski dispersion relation. This dominates. And also here the fluctuation dissipation relation is broken. Let me also say one word about the dispersion here. It seems to be a linear dispersion of this kind of transport peak, which is the same as in GPE. I have not shown you that. While this one is the Boguslavski dispersion, you see it's written in a slightly different way from what you're probably used to, because we are in a relativistic theory. So you have to make sure that at large momenta you actually have a linear curve, and this is actually exactly the way how you can approach that. It's kind of seems to be a generalization of the Boguslavski theory for non-relativistic scalars. Now let's go to O8 theory. So basically n large, a completely different picture. You don't have at all this kind of peak that is missing here. You always have one single peak, and this peak also is in spectral function and in statistical function. And this picture actually is valid for n equals 3, 4, 5, 6. So any n larger than or equal 3, which was also surprising. And the dispersion relation of this peak is just a relativistic dispersion, square root of m squared plus p squared. And so Thomas Gassenter had a theory that published a theory that for large n, one actually have some kind of Gaussian bosons with a p squared over 2m squared dispersion relation, which would be in a relativistic case square root of m squared plus p squared, and plus some chemical potential. And this seems to be working here pretty well here. Now, and this is also so when I was talking about this effective kinetic theory, what we actually use ad hoc without actually deriving that is not a Boguslavski dispersion for that, but actually a p squared over 2m dispersion, and it worked marvelously. You saw those pictures, and we didn't understand why it worked so well, because you should have actually a sound wave, so you should actually have a linear dispersion at low momenta, which we did not put inside the kinetic theory. So this explains why it works so well for large n. Now let's go to the most difficult case, and this is the n equal 2 case. Because this case has everything. You have basically, and this is what's really a surprise for us. So what you have is actually 4 peaks. Now, this is a Boguslavski peak. This one I did not even discuss, but that is also in the n equal 8 and so on. So this Boguslavski peak is, it has the usual Boguslavski dispersion relation. And now you have both peaks that we saw at n equal 1 and n equal 2. So this large n peak and this transport peak here. This non-quasi particle. This non-quasi particle peak is here. You see, there is no relation to the spectral function. However, this second peak, which is very close to that one, It has a relation here. So you see also kind of a bump here in the spectral function. And when you look at the dispersion relation for different, so basically you look now at different momenta, and you compare all of them, you actually even see that this is a linear dispersion here, while this is a quadratic dispersion. So basically, this is something, again, this is all that is preliminary. Well, not the results, but the the interpretation and all of that. So what we find are 3 quasi-particle peaks and 1 non-quasi-particle peak for n equals 2. And so for n smaller or equal to, actually this peak dominates this infrared part. So this infrared part. While for n larger or equal 3, this large n peak dominates that. But why you see completely the same dynamics for all n and for relativistic theory, it's still a mystery. But you just see that in the distribution function. But I think it is important to actually look deeper into the excitation spectrum to actually reveal what is universal and what is not universal. Okay, so now I come to my conclusion. I'm very, very sorry to be to have gone over time. So I will just leave my conclusion. So my conclusion is basically that you have that those systems very often, or actually usually, basically approach subsimilar attractors in this classical regime, and you have seen two examples of what one could interpret as universality classes. However, when you look deeper into that, the picture starts to shake a little bit. However, it's still intriguing, and then this is apparently something one has to go on and study more. The new method that has been developed to extract spectral functions, I think this is very, very interesting also to use not only for closed systems, but maybe also for open systems. This is something I would like to discuss with you. So basically what are potential applications? I'm sure there are many of those, but where to use this kind of machinery to get the spectral function to actually learn something about turbulence and other systems. Thank you very much.
We can have a few questions and then continue the discussion in the afternoon.
So in your quasi-particle spectrum, there's always a man, and you don't see sound waves in it, but couldn't you see sound waves with the energy correlation function?
I mean, yes, but we have not looked at energy correlation function exactly. So basically, these are all 2-point correlation functions in the field itself, not in composite field. While it is possible to do these kind of things, and this is something we would like to do, we would like to go on in this direction. That's why transfer coefficient and so on. We would like to get it from here, from the statistical function, basically from the undercommutator. Because the commutator is a bit more complicated, and we are not completely sure so far how to set up the theory to do the correct linear response in order to get the commutator of the energetics. But at least from this one should get it. And as we saw, this seems to have even more information in the spectral function. So this is for sure something that we want to go to in all those different systems in the future.
Other questions? Okay.
Just sorry, going back to the early schematic and everything, and now having seen it, it's very nice, but how much sensitivity is there to the initial conditions about any of these scales? The point is that you can see that there's absolutely no sensitivity. Like whatever you start initially, it doesn't matter, because once you go to that point, you will always have the same coefficients as long as you're dealing with the same sort of physical regime.
Absolutely. So what we did is, for instance, and I'm sorry. Oh, here. I'm sorry. What we did? Should I change something?
Sure. No, it should be fine.
Anyway, I have not done any backup slides for that, but we started, for instance, with just the condensate and basically only some random fluctuations here, some very small things. This or basically having like different structures in momentum space and whatever. This all, you know, in any of those systems, we of course change initial conditions, and there is some transient regime which is different and which is also physical and interesting. But you know, to get to this non-thermal fixation. But at the non-thermal fixation, the closer you are, the closer your exponents and the scaling form becomes to some kind of universal form. But of course, there are always some corrections, some finite time corrections.
Okay, so let's thank the speaker once again.